Hello! Today we will be covering BERT. My name is Kay Ayala. Let's get started. What is BERT? BERT is an NLP algorithm that, at the time of its release, advanced the state of the art on 11 NLP tasks. What is BERT used for? Classification, named entity recognition, part-of-speech tagging, and a whole host of other natural language processing tasks. What is BERT not? BERT is not a language model, a text generator, or a translator by itself. What we have here are 3 different leaderboards, each for a different data set for a different natural language processing task. Squad 2.0 is the Stanford Question Answering Dataset version 2. GLUE is the General Language Understanding Evaluation dataset. SuperGLUE it calls itself a stickier benchmark for general purpose language understanding systems. On these leaderboards, we can see algorithms such as Albert, StructBERT, MacBERT, PyAlbert. These are all successors of BERT. Let's look at the historical context of BERT. We can see here that there are quite a number of algorithms that directly pertain to the history of BERT. If you're interested in looking into the history of natural language processing, some of these algorithms are going to be really important for you to know, at least know in the context of NLP history. The transformer here. This is super important in terms of the history of BERT. We will be covering the architecture of the transformer in just a minute. You can also see some successors of BERT here. Roberta, Albert. Albert's the one that we saw on all the leaderboards. Many models have come out since the advent of BERT that are either direct successors of BERT or challengers to the successor of BERT. They are not all going to be listed here. There are way too many. Let's take a look at the architecture of BERT. In order to do that, let's see what BERT stands for. The Pre-Training of Deep Bidirectional Transformers for Language Understanding. What are we looking at? That's the BERT architecture. Here, we have something called word embeddings. Word embeddings are a vector representation of a word that usually encodes more content about the word than the word has by itself. We'll be getting more into this later. TRM, that stands for transformer. The transformers here are different than the transformers published in the paper Attention is All You Need in some small but significant ways. TN, this is our output. The output from BERT is a little tricky. We'll be covering it more later. For now, we will be looking at what is a transformer. In order to understand what a transformer is, we need to go back to the Attention is All You Need paper published in 2017. There we go. That's the transformer. What's going on in there? Well, inputs going into an input embedding, adding in a positional encoding, we'll describe later how that's made, which goes into multi-head attention, also going to be described later, through an added normalization layer, through a feed forward layer, another added normalization layer, and then we have this right-hand side. This left-hand side, this is called an encoder, it is called a decoder. So the encoder is this whole section here, the encoder. This whole section here, this is the decoder, just the boxes. So that's what a transformer is. But how is this transformer different from this transformer? What makes this transformer different, even though we still call it a transformer, and even though we're talking about it, we still talk about attention, as you'll see in the literature, is something a little strange. We don't have this entire right-hand side of the transformer. All of the decoder architecture, all the second layer of inputs, this extra feed-forward network, linear activation, the softmax, and output probabilities, we don't have any of it. We do have the encoder, we do have the input embeddings, and we do have a positional encoder. The difference is we just have a big stack of these. And that's something I should mention about these right now is, see this NX term right here? What that means is we can stack these up as many times as we want. They have a particular number of times they stack them up, a certain number of encoders all one on top of another, and a certain number of decoders all on top of another. In the attention is all you need paper. Bidirectionality. Covered what transformers are. What does bidirectionality mean? Bidirectionality refers to all these arrows in here and how information from one word influences the processing of the information from another word, and it happens both left to right and right to left. This is different from the historical way of doing it. For instance, let's take a look at the architecture of OpenAI's GPT. Do you see how these arrows only ever point to the right? They come from the left, go to the right, just like how we read. This is called a left to right model. This is called a bidirectional model. This only gets information from words previously in the sentence. This gets information from the words before and after the word that is currently being considered. We understand now generally what bidirectionality and transformers are, but what does pre-training mean? Why doesn't this just say trained or assume that it's trained like we would with any other model? BERT has so many different language tasks that it can excel on because of this pre-training architecture. Really what this is this whole section here, the transformers, the embeddings, these are just outputs, goes into another layer here. And this layer we can strip off and put on a different one and train this whole thing for something else. The magic of this is that these layers are all pre-trained for us. So when we add on these other layers at the end, our total training time is greatly reduced. And that's exactly how they trained the BERT model, is they trained it on two different tasks. One was next sentence prediction, and the other was something called the masked language model. The reason we have the masked language model is so that the model doesn't somehow cheat in learning because of the bidirectionality and getting information from both sides of the word. In the OpenAI GPT architecture, they didn't have this problem and they were able to train it in different ways. Let's take a different look at BERT's architecture. This one is a little bit different from the one we saw previously, where transformers were broken down into individual units. This shows transformers as a layer, and it'll make a lot more sense when we look more in depth at attention here in a minute. Each of these transformer layers has a depth of 1 encoder. So we are essentially 12 encoders deep before we hit our final model fine-tuning layers. Let's start at the beginning. Here we have 2 sentences. Sentences are a term that's used a lot in the literature, but a sentence in this case doesn't mean a sentence in the classic sense. The sentence in the literature means a segment of text, and in the BERT paper it says they are quite often longer than a sentence typically is. So keep that in mind if you go digging. Okay, so then these get tokenized. We'll discuss what that is later. Made into word embeddings. Also, we'll discuss later. Put through our transformer layer. Output of that comes out, goes into our next transformer layer. Output all the way through for 12 transformer layers, specifically 12. The first author on the BERT paper said, in doing ablation studies on previous models, the thing that he found to be most important about the viability of the NLP model was its depth. So that's why he decided to make this model particularly deep. So 12 layers. Output. We can think of this next section as just an opportunity, a place that is an opportunity for future layers. Task specific layers. In this case, we're seeing an MLM classifier and an NSP classifier. What does that mean? That is the mass language model. So let's say we went through and we're like, oh, we're going to mask out this word, and we're going to have the model guess what the original token actually is. That's what this is doing. And we could do it in multiple different places. The NSP classifier is next. Okay, what it's asking is, does this sentence make sense to follow this one? That's all this is asking. And of course, those go here. This is what the pre-trained BERT is trained on. And then we can remove this, add in whatever other final layers we want for whatever specific task we want. Okay, let's take a second to look at an overview of the encoder structure before we dive into attention. Very roughly, this is what an encoder is. It's a self-attention layer followed by a feed-forward neural network. Yes, there is a normalization going on in there that I'm not showing. Why are we calling it self-attention? We call it self-attention because if we look over here at our input, really what we're asking with attention is, how do I want to weight each of the words in this vector in order to make it easiest for the final model layers to classify, or whatever other task I want it to do. And that weighting is what we call self-attention. And we are paying attention to the input sentence, which I guess we are thinking of as ourself. We are paying attention to ourselves. Now, let's take a little bit of a more specific look at what this is. Okay, zoomed in a little bit more. What that looks like is an attention layer, followed by a normalization layer, followed by a hidden layer, followed by an output and normalization layer. All right, at long last, let's take a look at what attention is. The kind of attention we're using is called scaled dot product attention. It is a function of Q, K, and V. It's equal to the softmax of Q dot product K transpose over the square root of the dimensionality of K times V. Let's break that down as vectors. Our input here is thinking machines. We convert both these words into word embedding vectors, which we're representing here simply as X. We have 3 new vectors here per word: query vector, a key vector, and a value vector. As far as I found, these are arbitrarily named for convenience. I've heard it hypothesized that each of these explores a different semantic meaning in the initial word itself with the context around it. However, I've yet to see that written in a paper. Let's see how to build these vectors. We have 3 matrices of trainable weights. Here, WQ, WK, and WV. Each of these matrices produces their respective vector. So WQ produces the Q vector, which is the query vector, and so on for WK and WV. We produce them simply by taking the dot product of the word vector by the weight vector, which is equal to the resultant vector. Let's step through the dot product. We have this first row here, and we are going to multiply it by our word vector, and that is going to give us the first entry in our resultant vector. And we go through and we take the next column in our weight matrix, and again multiply it by our word vector, and we get our next element in our resultant vector, and same thing for our last column. We go through and find the dot product between the word vector and the respective weight matrix for each weight matrix to find the remaining vectors. It's important to note here that as we're doing these multiplications, we're doing them against the first word, and that's producing this whole column. We're also going to do it against the second word and produce this whole column. All right. Now, as we're doing this, we can see that the cue we're working with is from the first word. This is important because it makes us realize that what we're doing here, we're getting pairwise information about the words. All right, what we're doing is we're looking at this term here as we incorporate it into the entire term inside the parentheses. Let's take a moment to recall what the softmax is. Two things to note about the softmax here. It sums to 1. 2, the softmax score determines how much each word will be expressed at this position. So what does he mean by position? So as you notice, we're evaluating this whole thing for word 1. The position refers to which word we're currently at and how much the context around that word factors in. These ones, same as these. Just copied them on down. And remember that these were made from a weighting or transformation on the word embeddings themselves. So we're taking a altered form of the information in those word embeddings for each word, and we're weighting it by the softmax score. Then we add them element-wise in order to get this final output vector. This is the vector for word 1. Repeat for the rest of the words in the input. Now that we've looked at this broken down as vectors, it's time for us to look at this in its matrix form. Step 1, projections. For our matrix X, we have word embedding 1 on top, word embedding 2 on the bottom. Same concept here. Take your first column, multiply by your row, and that's how you get your first entry. First column, second row, bottom left entry, or next entry down in the column. Next column, top, next column, bottom, next column, top, next column, bottom. And repeat for WK and WV. There you go. That's the same thing as that right there, but in matrix form. So what does that mean? It means instead of doing every single vector independently, we've stacked them up and we're doing them all at the same time. So we are processing both words, or rather all the words, in the input at the same time. Scoring. Exact same thing as right here, but in matrix form. And it's really handy of them, it's very handy of them to have included the fact that K is transposed. They don't always do that. And so that's real nice. The softmax is just written this way in order to show that we're doing it over the rows. I'm arbitrarily calling this re-weighted scores, just for clarity when I write it down in the next line. Nowhere does it say that, and it may not be technically correct to call it that. It's worth noting that I am leaving out the division by 8 here, or rather the division by the dimensionality of K. It is just a very small operation. Everything that happens here, I actually forgot a thing here. This is supposed to be multiplied in like this. You take the softmax, weight V by it, add the V's together, and you get Z. And that is exactly what we're doing right here. And note that Z contains information from all the input words scaled by attention. We have Z1, and that is the output of one attention head. But in each transformation layer, we have 12 attention heads, and that's why we call it multi-head attention. Now, how are those attention heads arranged? They're all in parallel. They're all side by side. So all we have to do is take all of the z vectors and concatenate them all together. Now, it's worth taking this moment to note that this is not the actual size of the z vector. They are not 2 by 3. They are quite a bit larger. This W0 here is a dense normalization layer. We consider this to still be part of the encoder block, and you can see it in the transformer is all you need architecture as an add and norm layer. The matrix that comes out of this dot product is what we then feed into the feed-forward network layer. Now let's go back to the BERT architecture. So back up at the BERT architecture, here we have this transformer layer, and when we take a deep look at that, we see that it's composed of self-attention and a feed-forward neural network. Okay, so this is what we were just looking at right here. We had our attention layer. This is our multi-headed attention, where the output of this is concatenated. Our normalization layer is that multiplication by the WO weight matrix, and then that is fed into our feed-forward neural network, and that's composed of a hidden layer, an output layer, and a normalization layer before the output of this is fed into the next transformer layer. So what we have here, and it's not shown, but each of these has 12 attention heads in it. Then we have 12 layers of these. So overall, we have 144 attention heads. So to recap, words into word embeddings into transformer layer goes to 12 of those. The output of that is then fed into these task-specific final layers, which then output your final result. Also, if we take a look back over here, this is going to make a lot more sense now. So we have our multi-head attention, our add and norm layer, feed-forward neural network, add and norm, and then we don't have this because it's BERT. We have our input embeddings, our inputs, but this positional embedding, we haven't covered that yet. Nor have I really talked about input embeddings. Let's do that. First, what we do is we take our raw input words and then we tokenize them. So what we have is our input text. We feed it through a tokenizer, and what that does is we take each word and we break it up, including the punctuation, into these subsections. Now, how this is done is really dependent on the task and the tokenizer being used. While this example extracts out this dash as its own token, other tokenizers, they may just completely cut that out. And we can see this again here where 500,000 is broken up into 500, 000. Let's consider a possible input. So these are words that have been tokenized. You can see there are some strange tokens in here. We have this CLS in brackets and this SEP in brackets, and SEP at the end. SEP denotes a break between two segments, often referred to as sentences, even though they aren't necessarily sentences. And then CLS goes at the beginning of any input that we're going to use for classification. We also see here token with 2 pound signs and then ing. This happens anytime we have a word that's broken up into multiple parts. We get this double pound sign combination right in front of any of the word chunks that come after the first word chunk. So play doesn't have one, ing has one. If there were more after ing, they would also have the double pound sign. Okay, what BERT does is it then takes this and it makes it into a word embedding, which is also called a token embedding. And the way it does it is it uses a algorithm that converts from tokens into vectors. So the vector contains information about word similarity for their semantic meaning. So if there are two words that are close together, semantically they'll be more related. If they're two words that are far apart, they will be less related. Let's take a look at what that looks like. So as we can see, forest and woods are closer to each other than they are to couch and sofa are very close to each other. So this we can think of as a vector space, and the address essentially of every vector is the word embedding itself. And the way BERT does this is it has a dictionary of 3,000 words in its vocabulary, and it takes the tokens and finds their predefined word embedding. If they can't find a word embedding, then it has a process of breaking up words into their constituent parts, potentially even down to the letter level, in order to encode that word. Those are our word embeddings, aka token embeddings, but we still have two more kinds of embeddings. One is the position embedding that we've already seen outlined in some of the model architecture, and there's another one that we haven't mentioned yet, and that's called a segment embedding. And this one just shows which segment the word is initially part of, because otherwise the model wouldn't have any concept which quote-unquote sentence a word is coming from. Position embeddings. They tell us where in the length of the input a particular word is from. So what we do is we take all three of these embeddings and we add them up element-wise, and that becomes our input into the first encoder. Position embeddings. Let's take a closer look at those for a second. For the transformer in Attention Is All You Need, it uses two formulas. One is sine-based, the other is cosine-based. Let's take a look at this graph here. We have elements of the word embedding going from left to right, and from top to bottom we have all the words in the input. In this graph, what it shows is if we do it the way the paper says, and alternately use the sine and cosine formula to calculate position on all the elements here, this is what the graph should look like. However, Jay Alamar dug into it, and in the Google code, we can see that sine comes first and then cosine, and in the graph of it here shows that for the first half of each word embedding, they use a function that uses sine for position embedding. And for the second half of each word vector, they use the function that is based on cosine. Yet to completely throw another wrench in the system, if we look at the BERT paper itself, what it says is, quote, learn the position embeddings. Now, if we're learning the position embeddings, we don't have a pre-made function for them. We're learning them as part of the training of the network, which implies that we're not using the two sine and cosine functions that we've already seen. Now, with a little bit of space that we have left, let's investigate what BERT looks at. This is a fraction of an example taken from a paper investigating what BERT's attention heads quote-unquote look at or weight highly. So here we have the input sentence, and we have it copied again to show where attention is being directed. So there we can see for each word in the input, the weight is disproportionately being directed towards the SAP token. Here's an excerpt from the paper, What Does BERT Look At? An Analysis of BERT's Attention, where the authors investigated BERT's 144 attention heads, and they write, BERT's attention heads exhibit patterns such as attending to delimiter tokens, specific positional offsets, or broadly attending over the whole sentence, with heads in the same layer often exhibiting similar behaviors. We find there are common patterns in their behavior, such as attending to fixed positional offsets or attending broadly over the whole sentence. A surprisingly large amount of BERT's attention focuses on the delimiter token SEP, which we argue is used by the model as a sort of no-op. Generally, we find that attention heads in the same layer tend to behave similarly. For those who are wondering, a no-op is a piece of code that doesn't do anything. They continue. Then we evaluate the ability of the heads to classify various syntactic relations. While no head performs well at many relations, we find that particular heads correspond remarkably well to particular relations. For example, we find heads that find direct objects of verbs, determiners of nouns, objects of prepositions, and objects of possessive pronouns with greater than 75% accuracy. We then perform a similar analysis for co-reference resolution, also finding that a BERT head performs quite well. There are a lot more graphs of this nature in that paper, but there is not time, so I hope this description of BERT has been helpful for you. Thank you for watching. Here are the references.